Hello, everyone. Today we're going to continue with the trend of heating curves, but we're going to focus on calculations this time. Okay, before we continue, there's a new equation we need to know, and that is this one. Q is equal to mc delta T, okay? The M is mass. Okay, we all know what mass is. The C is your specific heat capacity, okay? If you remember from that one worksheet, specific heat capacity is how much energy you need to heat up a substance specifically by 1 degree Celsius. That's how they have it. That's how they define it. Okay. And let's look at one to give you an example. First, I want you to note something. So remember how I previously talked about how the length of the flat lines. So the length of the top flat line is a lot higher than the length of the bottom flat line. Okay, that'll give you an idea of how much energy you need to go from one state to another. So this is a lot longer than this, telling you that it's harder to heat up water, liquid water, than it is to heat up ice. And if we go to this table that's in here, we have the heat capacity for both ice, liquid water, and steam. And as you can see, liquid water is the highest. So out of all the states water can be in, when it's in the liquid form, it takes the most energy to heat it up, okay? It takes the most energy to heat it up. So that's specific heat capacity. And then triangle T, that's your change in temperature, okay? And I want you to think of Q. Q is energy, but you're going to see different terms for it. You may see the word enthalpy as well. So enthalpy, energy, leave that as Q, okay? It's the same, it's similar things. So think of Q in this case as energy or enthalpy. When you see a problem and this is enthalpy, refer to Q, okay? So now that we have that equation down, now we can start looking at some other stuff. Okay. So in this case, we want to convert ice to liquid water. The ice starts off at negative 15 degrees, and the water is at 25 degrees. So this is our starting point. This is our starting point, and then we want to finish here. Okay. What they recommend is drawing the graph. I will tell you this, you do not need the graph to answer these problems as long as you have these numbers. You can answer this question just using these numbers in the equation, but the graph can help you organize the information if you feel the need to do that. So let's do it their way first. So they sketch the graph out. Remember, you got to break it up into segments. So we're starting off at ice. To go from ice to water, we have to melt it first, okay? But before we melt it, we have to bring it to the melting point. Water freezes and melts at 0 degrees Celsius. So first thing we need to do is we need to go from negative 15 degrees Celsius to 0 degrees Celsius. That's what they do here. So here's our starting point. We're going from negative 15 degrees up to 0. Now we're at 0 degrees, okay? Ignore the time. I know they have it labeled like, oh, it took 6 seconds. The problem didn't give us any timestamps, but some time does pass. So ignore the values for the time. We don't know how much time passed, but we know that some time did pass. So they just labeled it like that for organization purposes, but ignore the time. So we went from negative 15 to 0. Okay, boom. That's the first segment. Now that we're at 0, now we need to melt it. Melting requires energy, okay? That's will be this one right here, heat of fusion. We have to use this energy in order to melt it. So the temperature isn't going to go up. Notice how from here to here, we're the same temperature the whole time, but we have to use energy to melt it, okay? So this is the second segment, we're melting it, okay? And then now that it's melted, we can go the final step. Now it's liquid water, and now we want to go from 0, which is where we were just at, up to 25, okay? They don't have it labeled, but if you follow along, if it did this right here, this is 25 degrees. That's the graph. Okay, so now you can see the graph visually. There are 3 segments total. So now when we go to do the calculation, you have to use the Q equation 3 times. Okay, what the graph can help what the graph can also help you with is tell you how many times you need to use the equation. For every line on the graph, that's how many times you need to use the equation. Okay, and with this case, we have 1, 2, we have 3 segments. Okay, we have 2 increasing portions and we have 1 flat portion. So that's 3 segments. We have to use the equation 3 times. The first time we use it, that's us heating up the ice. So this is the ice going from -15 to 0. The Q equation, we need mass, we need the heat capacity, and we need the change in temperature. The mass, the problem gives this to us, is 10 grams. The heat capacity, you can get from the table, 2.06 for ice. This is for ice. So 2.06. And then the change in temperature, we went from 0 to -15. So that's a total change of +15. What they're doing here is this is just final. This is the final temperature minus the initial temperature. That's what that is. So then 0 minus -15, subtracting a negative number is the same thing as adding a positive one. So this ends up being +15. You multiply everything out, and then you see that it took 309 joules of energy to heat up the ice. Okay? So now that's to heat it up. Now we have to melt it. To melt the ice, we need the heat of fusion. Okay? So the heat of fusion, this is for melting. It's for melting and freezing, but in this case, we're melting. You can do it in kilojoules per mole, or you can do it in joules per gram. Okay? So that you can use either or. Since the problem is in grams, we should be using the 334 joules per gram one. Okay? What they do here is they use the kilojoules per mole one, but they convert it to kilojoules per gram. I don't know why they did that. Or they convert the grams to moles. That to me would be a waste of time. This one, the bottom one, this would be the easier one. Okay, this would be the easier one. So you just take your heat of fusion and you multiply it by how much of the thing you have. So 334 joules per gram, multiply that by 10 grams, and you get your value. Okay, so in this case, it's 3,340 joules to melt the ice. Okay, I want you to notice that heating up took a lot less energy than melting. Okay, transitions always require a lot more energy than it does to heat things up. Okay, transitions take a lot of energy. So going from solid ice to liquid ice, that's how much energy we used up. And now the last step, now we need to heat up the water. Now we're in liquid water and we need to go from 0 to 25 degrees. Use the equation one more time. The mass is still 10, but this time notice we're using a different heat capacity. Okay, we're not using the 2.06 because now we're in liquid water. So now we have to use the liquid water heat capacity, which is 4.184. Okay, and then plug in the change in temperature. Again, they're doing final minus initial. Our final temperature is 25, and we started at 0. 25 minus 0 is 25. You plug everything into your equation, and we get 1,046 joules. That's how much energy it took to heat up the liquid water. You add everything up, and you get that your total change in enthalpy or your total change in energy is just the sum of all three, which comes out to be 4.7 kilojoules or 4,700 joules. Okay, that is how you do a heating curve calculation to see how much energy was required. Okay, and that's what you're going to be doing for today's worksheet. Okay, you're going to just be doing these calculations, trying to figure out how much energy was required. Okay, I'm going to do one with you. Let's see, are there any other examples in here? Calculate. Yep, okay. Okay. Let's do this one. We're not gonna, the answer is right here. Detailed answer to question 58. That's what we're gonna look at to see all the steps. So you want to calculate the enthalpy change. You want to go from ice to liquid water again, okay? So there's 3 steps. There's 3 steps. We have to melt the ice, but before we can do that, we have to heat the ice, and then we also have to heat the water, okay? So those are your 3 steps. We got to bring the ice to 0 degrees, then we got to melt it, then we got to bring it up to 22 degrees, okay? So that's a 3-step problem, okay? That's a 3-step problem. First step, second step, third step, and then they just add it up, okay? Mass is 75, plug in the 75. We're at ice, so we need the specific heat capacity of ice, which is 2.06, and then we need the change in temperature, which is positive 11. 0 minus, this should be, that's a typo. That should be 0 minus negative 11, and then you're subtracting a negative, so this will come out to be positive 11, okay? That's positive 11. Plug that in, they said they get 1700. That's the first step. Second step, now we have to melt the ice. Melting it, we need the heat of fusion. Heat of fusion is 334. How much do we have? 75 grams. Multiply it out, you get your value. Third step, now we need to heat up the liquid water. Again, we have 75 grams. Now we have to use the heat capacity of water, which is 4.184. And then what's the change in temperature? We're going from 0 to 22. 22 minus 0 is 22. Plug your numbers in, you get 6,900. And then the total change in your enthalpy, the total change is just the sum of all 3. Add them up, you get your value, comes out to be there. Okay, so that's how you do these equations. That's how you do these problems. And it's the same thing over and over. So it's just those calculations. So that's what we're going to be doing for today. Okay, let me do one with you, and then we'll call it. How are we doing on time? Okay, 12 minutes. Do I have enough room down here? I kind of do. Okay. So number 1, and I gave you all the information up here, so you don't have to look at the slides. All the information you need to answer all these questions are up here, so that you don't have to go back and forth to the slides. Okay. So heat of fusion, we want to know what amount of heat will change 82 grams of solid ice to, now we're going to vapor at 120 degrees Celsius, okay? So this is not a 3-step problem. This would be a 5-step problem. It's 5 steps, and here they are. So we have to bring the ice to 0 degrees. That's step 1. Then we got to melt it. That's step 2. After we melt it, now we have to heat up the water to 100 degrees, okay? Then we got to bring it to the boil. Okay, after we get it to 100 degrees, now we have to transition it into steam. And then after we transition it, we have to heat it up again to 120. Okay, so number one is a 5-step problem. Okay, this is a 5-step. So we have to use the Q equation 5 times. Okay, so the first one, I'm just gonna write them all up. First one, remember it's Q, or let me put this somewhere. Remember the equation, I'm just gonna put it here, is Q is equal to M times C times the triangle T. Mass times specific heat capacity times change in temperature. So let's do the first step. First step is heating up the ice. How many grams? We have 82 grams, right? Okay. So it's 82 grams times 2.06. I'm not gonna put the units because I really don't have that much space. times, what's the change in temperature? We are going from -6 to 0. So that's a total change of +6. Okay, that's a +6 change. Plug all your numbers in, plug that into your calculator, you get your value. Okay, and we'll do all that at the very end. Second step is now we have to melt the ice. So then you just take how much you have, which is 82 grams, and we multiply that by the heat of fusion. What is our heat of fusion? Heat of fusion is 334 joules per gram. Okay. Step 3, now we have to heat up the water. How many grams do we have? Again, the grams is always going to be 82. Now, what is the heat capacity of water? That will be 4.184. And then what is the change in temperature? We have to bring it to the boiling point. Water boils at 100 degrees. So we have to go from 0 to 100 degrees. 100 minus 0 is 100. So our change is going to be positive 100. Okay. The fourth step is now we have to vaporize it. Now we have to make the water into steam. So then that's going to be 82. And then instead of using the heat of fusion, now we're using the heat of vaporization, which is a lot higher, okay? Vaporizing takes a lot more energy than melting, if you look, okay? It's 2,260. So multiply that, you get your 2,260. And now the very last step is now we have to heat up the steam. We want to bring the steam to 120. So then again, it's 82 grams. Now we need the heat capacity of the steam, which is 2.02. 2.02. And then we need the change in temperature. We're going from 100 to 120. So that's a total change of positive 20. Okay. And now plug everything into your calculator. And let me grab mine, actually. Let me grab mine. I will be right back. Let me pause this. Okay. I'm back. So 82, 2.06. So this is going to be, this is 1,013.5. I'm just going to round it to one decimal to save time. 82 times 334. This is 27,338. 388, I'm sorry. Okay, then 82 times 4.184 times 100. This is 34,308.8. 82, 2260. This one's going to be the highest. 185,320. And then last but not least, 2.02 times 20. This is 3,000. 12.8. So by far the biggest contributor was the fourth step, which is where we are vaporizing the water, okay? Going from liquid water to gas, okay? That takes a lot of energy, okay? Now what you want to do now is you want to add all these numbers up, okay? Which I will do right now. 388, 3430, 8.8, 185,320 plus this. Okay, and we get a total of 251,343.1. This is joules. Everything is in joules. But the problem has the answers in what? The problem has the answers in kilojoules. Okay, so we have to divide that by 1,000. And we get 251.3 kilojoules. Okay. Now, let me see if I can find. This is how you do the problem, but from what I see here, the number I got does not match any of the numbers here. Let me see if I made an error somewhere. I'm going to pause this video too long and see if I can find my error. Okay, well, I double and triple checked and I don't see where my mistake was. I used all the units and numbers they gave me, but for some odd reason, my number doesn't match any of their answers. So I'm going to go with this portion, okay? If the other problems end up with similar things, then just pick the one that's closest, but that's interesting. I did exactly everything piece by piece. Numbers don't come up, but it's all good, okay? But this is how you do these problems. Break it up into steps, and then you do the energy calculation for each step. The only thing that's going to be changing is the heat capacities and the change in temperatures. If you notice, the mass is the same for all of them, like 82 is used in all of them. What's changing is the heat capacities. Once you go from ice to water to steam, it depends on what state you're in. And then pay attention to the change in temperature, okay? As long as you do that, you are golden, okay? But that's it for today. Just if you want to draw the graphs to help you, you can. But again, you do not need the graphs to answer any of these questions. Okay. My advice to you is to figure out how many steps you need and then set up those equations accordingly. I knew this one was 5 steps because it's going to vapor. Number 2, you're going from ice to liquid. We did that already multiple times. We know that that's 3 steps. Okay. Number 3, you're going from liquid to gas. Okay. And number 4, you're going from liquid to gas again. So look at the problem, see how many steps you need, and that's how many equations you're going to end up using, okay? But that's it for today. Happy Thursday. I wish you all the best. Take care and be safe.